Hey there, it's Shannon, Math Chick Myers, and today we'll be looking at section 13.3 in the Larson and Edwards calculus text, which covers partial derivatives. So we'll be finding and using partial derivatives of a function of two variables, a function of three or more variables, and then also looking at finding higher order partial derivatives of a function of two or three variables. So let's do it. Let's warm it on up by using our mad awesome derivative skills from Calc 1 to differentiate these problems with respect to x. On your mark, get set, go! You can do it. I know you can. All right, let's see how you did. For this first problem, I am going to opt to rewrite f by dividing through by x to the 1/2. So that's going to give us 3x to the 3/2 minus x to the 1/2 plus 2x to the negative 1/2. So now differentiating, we'll get f prime at x is equal to 9/2 x to the 1/2 minus 1/2 x to the negative 1/2, and then minus 1 x to the negative 3/2. Writing that as one happy fraction, let's go ahead and factor out a 1/2 x to the negative 3/2, and then we will be left with, let's see, 9x squared, and then minus x, is that right? Yes, and then minus 2 to get that coefficient of negative 1. And so at the end of the day, we will get f prime at x equals 9x squared minus x minus 2 all over 2x to the 3/2. Good so far? Awesome. All right, so next up, you can either expand this one out. I'm going to go ahead and use the chain rule. So g prime at x will be, so the most outside deal going on is something being raised to the 2 power. So you'd get 2 times your something to the 1 power. Your something is 5x minus 3, and you're going to have to differentiate that 5x minus 3 with respect to x, just in case you're a little bit rusty on the chain rule. So we'll get g prime at x is 2 times 5x minus 3. And then when I differentiate 5x minus 3 with respect to x, I will get times 5. So we will get g prime at x is equal to, so I think we'll get 50 x's. Does that look okay? And then minus 30. All right. And then let's see, again with the chain rule, f prime at x, the most outside deal going on here is that we've got the cosine of something. So differentiating, we'll have minus the sine of something times d dx of our something. So that something was x minus pi over 4. Continuing, we will have f prime at x is equal to negative sine at x minus pi over 4. And then the derivative with respect to x of x minus pi over 4 will be times 1. And so at the end of the day, we will have f prime of x is equal to negative sign at the quantity x minus pi over 4. Good, good. How are we doing so far? Awesome. All right, so now coming up on our first definition, partial derivatives of a function of two variables. If z equals some function in x and y, then the first partial derivatives of f with respect to x and y are fx and fy, defined by. So fx at x and y will equal our limit definition. And in our last section, I think we actually did a couple of problems using, found a couple of limits like this. So the limit as delta x approaches 0 of f evaluated at x plus delta x and y minus f at x and y all over delta x. And the first partial derivative of x with respect to y, what do you think we change? Beautiful. Now we evaluate the limit as delta y approaches 0 of f at x, comma, y plus delta y minus f at x and y all over delta y. Cool, cool? Provided, of course, that the limit exists. For the first problem, we'll go ahead and use that limit definition so that you can see what happens, and we'll also do that where we, treat the appropriate variable as a constant. And then for the second part B, we'll just go ahead and do it the faster way. So here, the partial derivative of f of x and y with respect to x would be the limit as delta x approaches 0 of, so the first is x squared, right? So we would have, well, your function of x and y is given, right? So wherever I see an x, I'm going to plug in an x plus delta x, and wherever I see a y, I will plug in a y when evaluating that first one here. Okay? All right, so now let's do it. So we will have x plus delta x squared minus 2y squared plus 4. So that's f at x plus delta x, comma y, and then minus x squared minus 2y squared plus 4. So that's f at x and y. And that's all over delta x. Cool so far? Awesome. So fx at x and y will be the limit as delta x approaches 0 of x squared plus 2x delta x plus delta x squared minus 2y squared plus 4 minus x squared plus 2y squared and minus 4 all over delta x. And look what happens. Everything zeroes out except for, let's see, the x squared zero out. Everything zeroes out with the exception of the terms that have delta x. So if we factor out a delta x, we'll be left with 2x plus delta x all over delta x. The delta x's divide out to be 1. And so now, using your direct substitution, what would happen? We would just get 2x plus 0. And at the end of the day, the first partial derivative of f of x and y with respect to x will be 2x. Cool so far? All right, so now doing this, as you know, by treating y as a constant, right? Let me go ahead and add a page. So remember that f of x and y was equal to x squared minus 2y squared plus 4. So if I want to find the first partial derivative with respect to x, you use this curly d, okay? And basically that tells you you're looking for your first partial with respect to x so that you don't differentiate a variable other than x implicitly. So what we'll have is this will yield fx of x and y, and then the first, just that partial derivative is a linear operator, just like regular derivatives. So you'd have the partial derivative with respect to x of x squared, and then minus the partial derivative with respect to x of 2y squared, and then plus the partial derivative with respect to x of 4. Now, the first one, and that first term, will just be what? Beautiful, 2x, right? But the other ones are going to, awesome, they're going to zero out because we're treating y like it's a constant. So at the end of the day, the first partial derivative of f of x and y with respect to x will just be 2x, just like we got with our limit definition. Cool so far? Okay, so now let's look at the first partial derivative of f of x and y with respect to y using the limit definition, and then we'll do the shortcut rule. So we'll have the limit as delta y approaches 0 of f of x comma y plus delta y, and then minus f of x and y. So this time what's going to happen is we'll just have x squared minus 2 times y plus delta y, the quantity squared, plus 4. So that's our f of x comma y plus delta y. And then minus f of x and y, which was x squared minus 2y squared plus 4 all over delta y. So then we will have the limit as delta y approaches 0 of x squared minus, I'm going to distribute the 2, so we'll get 2y squared plus 4, and that'll be actually minus 4 y delta y minus 2 times delta y squared plus 4 minus x squared plus 2y squared minus 4. That's all over delta y. So we will have the first partial derivative of f of x and y with respect to y will be the limit as delta y approaches 0. everything will zero out except for the terms with delta y. So I will factor out a delta y, and we will have minus 4y minus 2 times delta y all over delta y. So the delta y's will zero out. And then now we can use direct substitution for our delta y. And we will have negative 4y minus 2 times 0. And so our first partial derivative of f of x and y with respect to y is negative 4y. Cool, cool? All right. So now let's do it using the shortcut rule. So f of x and y, remember, was x squared minus 2y squared plus 4. And so if we evaluate the first partial derivative with respect to y, we will get, on the left, fy of x and y is equal to the first partial derivative with respect to y of x squared, which we will treat as a constant, minus 2 times first partial derivative with respect to y of y squared, and then plus that first partial with respect to y of 4. So this time, anything that does not have a y in it is treated as a constant. And so we'll get 0 and then what? Minus 4y plus 0. Which will give us the first partial derivative of f of x and y with respect to y is just negative 4x, which is what we got using our limit definition. Cool, cool? All right, so now let's go back and do part B. So here, again, if we want to find z x, okay, that's going to be equal to that first partial derivative with respect to x of sine at 5x times cosine at 5y. Now we treat the cosine at 5y term as a constant, so we will have zx will be cosine at 5y, I'm just treating that as a constant, and then when I differentiate with respect to x sine at 5x, what will I get? Beautiful. I will have 5 times cosine at 5x using the chain rule. So at the end of the day, zx will be 5 cosine at 5x times cosine at 5y. Cool, cool? Okay. Next up, we have the first partial derivative of z with respect to y. So now we'll have dy, okay, of our sine at 5x times cosine at 5y. So now the one that's treated as the constant would be the sine at 5x. And when I differentiate with respect to y, the cosine at 5y, what will I get? Beautiful. I'll get negative 5 sine at 5y. So, cleaning it up, we'll have zy is equal to negative 5 times sine at 5x times sine at 5y. Cool, cool? All right. So, moving right along, we will have part C. F of x and y is equal to the integral from x to y of quantity 2t plus 1 dt plus the integral from y to x of 2t minus 1 dt. So using properties of integrals, we can rewrite f of x and y as the integral from x to y of 2t plus 1 minus, if I switch the limits of integration, I flip the sign. So I'll go from x to y, and then I'll have this 2t minus 1 dt. Sorry, there was a dt here and a dt here. Well, now that I've got the same limits of integration, I can combine like terms. So I'll have the integral from x to y of 2t plus 1 minus 2t minus 1. And all of that will be with respect to t. So that cleans up to be the integral from x to y. The two t's zero out, and so we'll just get 2 dt. So now integrating, what would happen? We would get f of x and y will equal to 2t evaluated from t equals x to t equals y. So f at x and y will be equal to 2 times y minus x. Good so far? So now, well, what do? To find the partials, we would have fx of x and y will be 2 times, beautiful, the y will zero out, we'll treat it as a constant, and then minus 1, because we'll have the derivative with respect to x of x is 1, and we had a difference in between them. So fx of x and y is just going to be negative 2. Well, fy of x and y will be 2 times, good, we'll have the derivative of y with respect to y will just be 1, and then the x will zero out because we'll be treating that as a constant. So the first partial derivative of x and y with respect to y is just 2. Cool, cool? All right. So here we go. Notation for first partial derivatives for some z equal to f of x and y. So again, you use these curly d's. So if you would have dx of f of x and y, which is equivalent to fx of x and y, which is equivalent to zx, which is equivalent of, using the curly d's or calling them del's, ddx of z. Cool, cool? Okay, so you could look at d dy of f of x and y is equivalent to fy of x and y, which is equivalent to zy, which would be equivalent to, using the curly d's, ddy of z. Now, a lot of times we do that line to show what you're evaluating something at. So here you could take a look at if you had dz dx, and you want to evaluate this at some ordered pair AB, that would be fx at AB. If you had the first partial derivative of z with respect to y evaluated at some ordered pair AB, that would be fy at AB. Cool? All right, so here we go. Example 2, use the limit definition to find the first partial derivatives with respect to x, y, and z. Oh boy, here we go. So we'll have 3 problems relating to this. So get your limit tools out. So fx of x, y, and z will be, so we're evaluating this function at x plus delta x comma y comma z. So that would be 3 times x plus delta x squared times y, I'm treating y as a constant, minus 5 times x plus delta x times y times z, plus 10 yz squared. So that is our f at x plus delta x comma y comma z, and then minus f of x, y, and z is 3x squared y minus 5xyz plus 10yz squared. And that will all be over delta x. And bad teacher, what did I forget to do? Good. I forgot my limit notation. So we have our limit as delta x approaches 0. So fx at x, y, and z with a little algebra is going to be the limit as del x approaches 0 of. So we're going to get, 3x squared plus 6x delta x plus 3 delta x squared, and then times actually all of these would be times a y. You see that? So times a y, because you've got a y multiplied on the right and the 3 multiplied on the left. All right, so then we'll have 5 minus 5xyz minus 5 delta x times y times z, and then plus 10yz squared minus 3x squared y plus 5xyz minus 10yz squared, all over delta x. So hopefully if we did everything right, everything will zero out except for the terms that have delta x. So let's check it out. So we'll have fx of x, y, and z will equal to the limit as delta x approaches 0 of. So the 3x squared y is 0. And let's see, so I'm going to factor out a delta x. Since we have so many terms, I'll show what zeroes out. So the 3x squared y zero out, these 5xyz's, and the 10yz squareds. And then the rest of them can factor out at least one factor of delta x. So we'll have 6xy remaining from that first term. Then we will have plus 3 delta xy, and then minus 5yz all over delta x. So the delta x's will divide out to be 1, and with direct substitution, the first derivative of f of x, y, and z with respect to x will be equal to 6xy plus 3 times 0 times y minus 5 times y times z. So we're sending delta x to 0. And that gives us a final result of 6xy minus 5yz. Cool, cool? All right, so that's the first one. And now, finding the first partial derivative of f of x, y, and z with respect to y. Why don't you guys go ahead and give it a try and see how you do. Okay, let's see how it went for you. So we have the limit as delta y approaches 0 of 3x squared times y plus delta y minus 5x times y plus delta y z times z. And then we will have plus 10 times y plus delta y times z squared minus 3x squared y, quantity 3x squared y minus 5xyz plus 10yz squared all over delta y. Okay, so cleaning it up a bit, we will have the limit as delta y approaches 0 of 3x squared y plus 3x squared delta y minus 5xy minus 5x delta y, and both of those, I'm sorry, have z's in them on the right. And then we will have plus 10yz squared plus 10 delta y z squared minus 3x squared y plus 5xyz, and then, sorry, it's so scrunched, we'll have plus 10yz squared all over delta y. So let's see what zeroes out. The 3x squared y is zero out, and the 10yz squared zero out. And let's see, and the 5xyz is zero out. So we shall have the limit as delta y approaches 0 of, I'll factor out a delta y, we'll be left with 3x squared minus 5xz plus 10z squared over delta y. The delta y's divide out to be 1. And so, using direct substitution, we will have the first partial derivative of f of x, y, and z with respect to y is 3x squared minus 5xz plus 10z squared. Cool, cool? Awesome. All right, so let's do that last one. So I'll write small. The first partial derivative of f of x, y, and z with respect to z is equal to the limit as delta z approaches 0 of 3x squared y minus 5xy z plus delta z plus 10y z plus delta z, the quantity squared, so let me make sure my grouping symbols are all here so you guys can see what we did. And then subtracting from that, f of x, y, and z, we'll have 3x squared y minus 5xyz plus 10yz squared all over delta z. Okay, so fz of x, y, and z is going to be the limit as delta z approaches 0 of 3x squared y minus 5xyz minus 5xy delta z plus 10y z squared plus 20 y z delta z plus 10y delta z squared minus 3x squared y plus 5xyz minus 10yz squared all over delta z. So let's see what all zeros out. The 3x squared y's will zero, the 5xyz's will zero, and the 10yz squareds will zero out. Factoring out a delta z, let's see what we get. Almost done. we'll get the limit as delta z approaches 0 of, so we'll have a delta z times negative 5xy plus 20 yz plus 10 y delta z all over delta z. And with direct substitution, we will have fz at x, y, and z will be equal to, do you see these delta z's divide out to be 1? So we'll get negative 5xy plus 20y times z plus 10y times 0. And actually, do you see what the other one, this one right here, we didn't really need to directly substitute because it's simplified to something that had no delta z's in there. So I'm just going to go ahead and erase this one right here just to have, everything proper. So fz of x, y, and z will be equal to negative 5 times x times y plus 20y times z. Good? All right. So that one's all good. Here we go. So this one, my apologies. We've got to change the notation here. These need to be the curly D's, okay? Because they are partial derivatives. And so that's, just make that change in this one. So now if you've got a function of 3 or more variables, you're going to have the following partial derivatives. So if you've got w equals f of x, y, and z, then the first partial derivatives of f with respect to x, y, and z respectively are defined by all of these here. So remember, you're just doing, that's what we were doing actually on this last problem. I should have done that definition first, okay? So it does extend to 3 or more variables, right? And you would just keep going. I mean, with each successive one, you would just keep going. Actually, I should put in general. We should go ... So if you have w is equal to f of x1, x2, all the way down to xn, there exists n partial derivatives and those partial derivatives would be denoted by fxk of x1, x2, all the way down to xk, where k is equal to 1, 2, all the way down to n. So you would just keep going on in that manner until you had found all of the n partial derivatives. Cool? Okay, so now let's go ahead and we don't need to use the limit definition for this one. Let's go ahead and do it kind of with the faster way. So remember, when I'm finding fx, I am I am differentiating with, I'm finding the partial derivatives with respect to x. Okay, so everything else will be treated as a constant. So I'm going to use the quotient rule here, right? So the derivative of x and y with respect to x is just going to be, beautiful, y. And then you multiply by the denominator as it is. You subtract the numerator times the derivative of the denominator, and that's just going to be times 1, right? Because the plus y plus z will zero out. And that's all divided by the denominator squared. So, fx of x, y, and z, cleaning it up, let's see, we could factor out a y, and then you would get x plus y plus z minus x over x plus y plus z. So then we would have fx of x, y, and z would be y times y plus z over x plus, and I'm sorry, this is squared, the denominator is squared, or x plus y plus z, the quantity squared. Cool so far? All right, so now fx evaluated at 3, 1, negative 1 will just be 1 times 1 plus negative 1 over 3 plus 1 plus negative 1, the quantity squared. So all I did, wherever there was an x, I put in a 3. Wherever there was a y, I put in a 1. And wherever there was a z, I put in a negative 1. And that's just going to be 0, I believe. Right, because that numerator will be 0. So in the x direction, you would potentially have a point where there would be a relative extremum. Okay? All right. So that's the first one. So next up, the first partial derivative of x, y, and z with respect to y will be, again, we have to use the product rule. So this time we'll get x and then times x plus y plus z, the denominator, minus xy times, well, again, we'll just get 1, right? Because this time the x plus z will zero out. And that will all be over the denominator squared. All right, cleaning it up, we'll have, let's see, I think we can factor out an x this time. So we'll have x plus y plus z minus y. all over quantity x plus y plus z squared. So we will get Fy of x, y, and z will be x times the y zero out. So we'll have an x plus z all over x plus y plus z, the quantity squared. So now evaluating in the y direction, that derivative, the slope in the y direction, we're evaluating at what? 3, 1, negative 1. We will have 3 times 3 plus negative 1 over 3 plus 1 plus negative 1, that quantity squared. So again, matching up what I'm plugging in for. This time, the slope will be the slope in the y direction will be, let's see, 3 plus negative 1 is 2, so we'll have a 6 in the numerator, and over a 3 squared, which is 9. So at the end of the day, the slope in the y direction at 3, 1, negative 1 will be 2/3. Cool, cool? All right, and then actually the next one will be fairly easy, believe it or not, because since we're treating x and y as constants, what'll happen is this: we can write f of x, y, and z. We could write it as x times y times x plus y plus z raised to the negative 1. So now, finding that first partial derivative with respect to z of f of x, y, and z, we'll have x, y serves as a constant. Using the power rule, we'll have negative 1 times our something to the negative 2. And then our something is x plus y plus z. And then what are we going to need to do? We're going to need to find, our d dz of x plus y plus z. So fz, x, y, and z will be x times y times 1 over x plus y plus z, the quantity squared. And evaluating this at 3, 1, negative 1. So our slope in the z direction will be 3 times 1 over 3 plus 1 plus negative 1, the quantity squared. Cool. And let's see, we'll get 3 over 9. So FZ at 3, 1, negative 1 has a slope of what? It'll be 3/9, right? And actually, let me make sure. You know what I did? I lost my negative. Remember, I had a negative right here. So there would be a negative here. And so we'll get a negative 1/3. Cool, cool? All right. So now, let's take a look at some higher order partial derivatives. Differentiate twice with respect to x, right? So you'd have d dx of df dx, right? All partials. And that's equal to d squared f over dx squared, which you're going to commonly see it as fxx. Okay? If you differentiate twice with respect to y, this is what you'll have. That'll give you fyy. Now, if you differentiate first with respect to x and then with respect to y, you will have dy of df dx, which will give you d squared f over del y del x, and that ends up being fxy. Then if you differentiate first with respect to y and then with respect to x, you'll have fyx. Now, what you're going to find is that these two here, you're going to find that they're equivalent to each other, right? That they're equivalent. So let's find in these next couple problems. Did I have more than one? Yeah. Let's find the 4 second partial derivatives. Okay. So here we go. Zx, going a little faster now, is going to end up being, so when I do the first partial with respect to x, I'll have 1 over x minus y. Cool so far? And then zy will be, well, the derivative of the denominator with respect to y will end up being negative 1 over x minus y. So d dx of zx is going to be what? I mean, isn't zx equal to x minus y to the negative 1? And zy is equal to negative x minus y to the negative 1. So I would have d dx of x minus y to the negative 1. That's going to give me zxx, right? That's what I want for that one. So then I would get negative something to the negative 2 times the derivative, first partial derivative of that something with respect to x. And so we would have zxx is equal to, good, we will have a negative 1 over x minus y squared. Cool, cool. All right, so that's zxx. How about zyy? What's that going to be? Actually, so now if we do that first partial with respect to y, and we do it to zy, that will give us that first partial with respect to z of negative x minus y to the negative 1. And that's going to give us, let's see, that's going to give us zyy is equal to, well, we will have negative something to the negative 2 times dy of our something. Well, the something that we had was x minus y. And so zyy will end up being negative 1 over x minus y, the quantity squared. So zyy will just be 1 over x minus y, the quantity squared. Cool, cool? All right. So now, here we go. If I want to find zxy, right, remember that I find dy of zx. Well, that's going to be dy of, what was our zx again? 1 over x minus y to the negative 1. So zxy will be, what are we going to get for that? Well, we will get negative, I'm going to go a little bit faster. So we're going to get, oops, sorry. This will be, using the power rule, we'll have our negative 1 times our something to the negative 2. Our something is x minus y. The derivative with respect to y of x minus y, the first partial, would be negative 1, right? So it turns out that zxy is equal to 1 over x minus y, the quantity squared. And our last one to check out would be zyx. So now we do ddx of zy. Well, that's going to be the first partial derivative with respect to x of, let's see, zy was negative x minus y to the negative 1. So what's going to happen is we'll get zyx is equal to negative times a negative, you know, or if you want, you can keep the negative there, times negative of our something to the negative 2. And then let's see, the derivative of the inside with respect to x is just going to be a positive 1. And our something was x minus y. And so, cleaning it up, what's going to happen, we're going to get our zyx is equal to positive 1 over x minus y squared. And notice that they match, right? So you're always going to get zxy is equal to zyx. Okay? And so notice that these are the same. Okay, so with the arctangent function, let's see what we will have. Probably need to add a page. We'll see what happens. So, arctangent of this is equal to arctangent of x to the negative 1 times y, right? All right, so when we're differentiating the arctangent, the first partial with respect to x is we need to differentiate what's inside the arctangent with respect to x. So do you see that we would end up getting negative x to the negative 2 times y, and then over 1 plus what's inside there squared. So we would have we'll end up with negative x to the negative 2 times y over 1 plus x to the negative 2 times y squared. Let's see if that'll simplify a little bit. This would end up being negative y over x squared times 1 plus y squared over x squared, which would be negative y over x squared plus y squared. Cool so far? All right. So, geez, these will be kind of a pain. Let's go ahead. We'll have to add a page. Let's copy what we have here. Or better yet, bring it, no. Copy, we'll copy it. Okay. All right, so now working with this one, we found our ZX. Just for form's sake, this will also be equal to negative y times the quantity x squared plus y squared to the negative 1. Cool so far? All right. So zxx will be what? Good. We'll end up having negative 1 times negative y is positive y, and then we're going to have x squared plus y squared to the negative 2, differentiating the inside of those parentheses with respect to x, we'll have times 2x. So zxx will end up being y, let's see, 2xy over x squared plus y squared squared. Cool, cool? All right, so how about zy? Zy is going to be beautiful. The derivative of x to the negative 1 times y with respect to y is that partial derivative is just going to be x to the minus 1. And then over what? Good, we'll get the same here. 1 plus x to the negative 1 times y squared. And so that will be 1 over x times 1 plus y squared over x squared. And that in turn will be 1 over x. I'm going to get a common denominator, so we would have x squared plus y squared over x squared, right? And so this will divide out one of these. And so at the end of the day, inverting and multiplying, I believe, we will have x over x squared plus y squared. Hopefully I did the algebra right. And that, of course, could be written as x times x squared plus y squared to that quantity to the negative 1. So zyy is going to be negative x times x squared plus y squared to the negative 2, and then the derivative with respect to y of x squared plus y squared is 2y. So that will be negative 2xy over x squared plus y squared squared. Oh, that's interesting. So they're just going to be opposites of each other, those two derivatives. So this was our zxx, and this here was our zyy. Now we need to remember that zxy equals zyx equals. So let's see. It's going to be pretty similar. Why don't we just go ahead and take the one that doesn't have a negative, which is zy. So let's go ahead and find the first partial derivative with respect to x of zy. Actually, let me do this vertically. So now we will do d dx of, so zy was x times x squared plus y squared to the negative 1, right? And so differentiating that with respect to x, we're going to have to use you could either use the product rule. Actually, you know what? Let's write it like this. I'll just use the quotient rule. So d dx of x over x squared plus y squared. All right, so differentiating with respect to x, what are we going to get? We're going to get 1 times the denominator, x squared plus y squared, minus the numerator times the derivative of the denominator with respect to x, which will be 2x, all over the denominator squared. So we'll have x squared plus y squared squared. Cool so far? So now this is going to be, so when you combine like terms, you have 1x squared minus 2x squared. So I think we'll get y squared minus x squared over x squared plus y squared squared. And we're good, because remember that the zxy equals zyx. Groovy? All right, so that's it. We're all done for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Bye.